Welcome to the morning session. I just got a message from our first speaker, Bo. He will be in a minute. So we will have two talks first. Let me just briefly talk about the schedule. So the first session is 85 minutes for two talks. So each speaker will take about 40 minutes. And during those 40 minutes, if you have any questions, you can just type them online, or we can just ask questions after the talk, but that's only within the 40 minutes. And then after that, we have from 11:20 to 11:25 for 5 minutes. We can use this for floor discussion or the question for the speakers. After that, we're going to have about an hour for the discussion on the formulation of the working group. So that's the outline. I'm not sure if Anne Bo is here, but let me start to introduce him. Professor Bo An is a President's Council Chair, Associate Professor in Computer Science and Engineer at Nanyang Technology University, Singapore. So it's really late time in Singapore. I really appreciate it. He can be here. He received the PhD degree in computer science from the University of Massachusetts, Amherst. His current research interests include artificial intelligence, multi-agent systems, computational game theory, reinforcement learning, and optimization. Dr. An was the recipient of the 2010, I really don't know how to pronounce this, IFAAMAS Victor Lesser Distinguished Dissertation Award, Operational Excellence Award from the Commander, 1st Coast Guard District of the United States. The 2012 informs Daniel H. Wagner Prize for Excellence in Operation Research Practice and 2018 Nanyang Research Award. His publication won the Best Innovative Application Paper Award at AAMAS 12 and the Innovative Application Award at IAAI 16. He was invited to give an early career spotlight talk at IGCAI 17. He led the team which won the 2017 Microsoft Collaboration AI Challenge. He was named to IEEE Intelligent Systems AI's 10 to Watch list for 2018. He's a PC co-chair of AAMAS 20. He's a member of the editorial board of GAIR and the associate editor of GAAMAS, IEEE Intelligent Systems, and ACMTIST. He was elected to the board of directors of IFAAMAS and the senior members of the AAAI. So, Bo, are you here now?
Yes, can you hear me?
Yes, now it's, yeah, I see your screen. So yes, please,
okay,
yes,
great.
You're right on time.
Yeah, so can I get started?
Yes, please. And if during the middle, if you have any questions, please just type them in the chat window. Otherwise, we're going to ask both questions after his talk. Please get started.
Thank you so much, Ray. I guess it's my honor to be here and share with you our recent research on reinforcement learning. I guess I have a background in artificial intelligence, so I guess I'm pretty much doing so-called UC-inspired research. So we're motivated by real-world problems, either in industry or societal challenging problems. And we're driven by these problems, and we try to model it, and we try to solve it, and in the end, we try to deploy the system or software, whatever, to make a difference in the real world. So I guess we are, I think, more application-driven RL research or AI research could be quite different from the audience who might work on more abstract models, mathematics, not statistics, this type of things. So what I'm going to do in the next 35-40 minutes, I'm going to share you our recent work on solving competitive and complex AI problems, and I will show there are two paradigms of work. One, we try to apply model-based approach and try to solve those optimization problems. The other is we go to reinforcement learning and try to use reinforcement learning as a tool to solve those problems. So I'm going to talk about many different pieces of work. I know the audience is of very different background. So what I'm going to do is I might just cover the high level idea of their approach, and I will spend more time to talk about what is their problem and why that problem is important, why it's challenging. So let me get started with AI in complex or competitive environment. I think basically AI is about study and construction of rational agents based on the Bible book of AI. And the early days of AI, people focus on building a single agent. So those days, people are more logic-based approach or doing planning. And from 1980s, people realized that lots of times the AI system could be distributed. They could be physically distributed. So we have to really think about how a distributed AI system could collaborate and to coordinate. And then after 2000, so because of the internet, the e-commerce is becoming more and more popular. Then people start to analyze in those kind of competitive environment how agents should interact and how can we design good policy. So that's another branch of research in the multi-agent systems. Um, so I guess when we talk about competitive environment, people often first think about applying game theory, as we know that game theory is basically a tool for analyzing interaction among multiple competing agents. I will only spend time to talk about that. So I think in terms of, I guess there's some chance. Let me look at what are those. Okay. So, so for solving competitive environment AI, those problems, there has been quite some success in terms of applying game theory to solve those problems. I will briefly talk about computer poker. That's something where basically algorithms for solving games can be applied to design the best software to beat the best human player in poker. I will also talk about some other things like security or under auction. We know those types of things which game theory play a major role. As I mentioned earlier, there are pretty much two major paradigms to solve this problem. One is algorithmic game theory. So, or we could say those are optimization problems, and people are using operations research, those type of ideas like solving large-scale optimization problem or algorithm design, designing efficient algorithms, maybe a approximate algorithm to solve that. I mean, that's one paradigm. And there are some successful stories which I will mention very soon. And I will also talk about many problems where we're not able to exactly model or we're not able to exactly solve. And for those problems, maybe we have data. And another approach often used is applying reinforcement learning, which can, for instance, if there are lots of data, maybe we can use the data to build a simulator, or without a simulator, we can still use this data to train a good policy. And then there we can apply those type of policy to the real world. So that's another paradigm. So I will start with some of our recent work on the first paradigm, applying computational games here to solve AI problems in a competitive environment. So I will mention about poker because this is something which is amazing. I guess the most successful story after AlphaGo. I will briefly, so this is a team of people from Carnegie Mellon, led by Professor Thomas Sandholm. They built the best poker player which be the best human player. And this problem, poker basically, it's more complicated than Go in the sense. Technically, this is something called incomplete information game in the sense that for Go, if you need to do decisions, the only thing you need is what's going on the board. But poker, we have partial information about other players' cards, and those are private information. So if you want, the difference between poker and Go is you have to analyze those incomplete information, which makes the problem more complicated. So the sniper task system builds on many key ideas. For instance, abstraction, and then the abstract the original game, which is a big game, into a small game and solve that game and do kind of reverse model to find out what strategy to play in the original game. And this is kind of offline computation, but they also do lots of online solving as well to further improve the efficiency. And one, so if you're interested, you can go to Thomas and Holmes' webpage to find more details. I want to highlight that this has nothing to do with deep learning, and which is amazing because we are able to see that actually there are approaches which can do far more better than deep learning based approach. So originally the computer poker player, I mean this Libertas is only for 2-player game. So basically the Texas Hold'em has only 2 players, and we know that in casino often there are many players. Actually, all the theory behind this computer poker is only for 2-player game. So all the theoretical foundation does not hold anymore for multiplayer poker. So multiplayer poker has been a hot topic. I mean, it's a difficult topic for computer poker community. So I guess we did some work on this. Basically, we are inspired by Thomas and the work in, I guess, Europe, maybe in 2019. They studied this multiplayer poker because it's too complicated. This started with a simple version. So they assume that if there are n players, they divided those n players into 2 teams. One team has only 1 player, and the other n-1 players, they play together. They want to beat this single player. So this is still complicated because those the n-1 players, they cannot communicate during the game, so they have to come up some policy to compute this policy, coordination policy, before the game starts. So we did some work to improve the efficiency of those algorithms for games within a team and 1 single player. The solution concept is called something called team max-min equilibrium. So we came up some efficient algorithms to solve to compute the equilibrium, which is based on a few techniques, such as we transform the non-convex problem into some MILP, and still we will also kind of do approximation to discretize those bilinear terms to do approximation, and then we're able to bound the approximation error, and in the end, the algorithm with performance guarantee and still is super scalable as compared with all the existing approach. So this is what we did this year. Another piece of work we did this year is we use another idea called something called kind of double oracle framework, or calling generation or row generation in operations research to solve large scale game. And this idea is quite often used in solving security games and many other domains. But if we want to apply those ideas to solve computing, to compute team max-min equilibrium, and actually it does not work. So there are so basically those will fail to find out the equilibrium. And we have some false results and why it will fail, and we analyze why it will fail and come up a new approach which can guarantee the algorithm will be able to converge to a T max mean equilibrium. So this is something new, and also we are able to beat all the state-of-art algorithms. I guess this is still kind of one step in multiplayer poker or multiplayer game. I think people are still working hard to solve this problem. This is still an open domain, and many people are working on that. So this is something we did for kind of micro game using optimization techniques or game theory OR approach to solve this problem. So there are some other work we did, for instance, in kind of in games. Sometimes we have lots of uncertainty about the other player. So one idea you could use, simple idea you could use is you could learn, for instance, you try some strategy and you get some feedback. And from the feedback, you might be able to infer their private information or get more accurate model of the other player. But this might be manipulated by the other player, because if they know that you're using this learning algorithm and try to learn their private information, they might want to do some manipulation so that they may not behave truthfully. So this is something we're trying to address in some work we did last year to how, given that the opponent is able to manipulate, how can we derive a good learning strategy so that we're able to achieve the best performance? So that's something which could be quite real and some important problem. We recently did some work on still solving large scale games kind of the using automata, this type of machine to simplify the strategy space, and we're able to achieve far more efficient algorithm as compared with the state of the art. So I guess it somehow showed for AI problems with in competitive environment, one way is model those as a game and using different techniques to solve this problem. And we're able to apply those back to the real world. And another paradigm is something called RL, which is the focus of this work, this theme this morning. So I will spend more time here. I guess I'm trying to think about when we need RL. In my feeling, RL might be more appropriate if the problem cannot be well modeled. So we talk about game theory. If you want to work on a game, you should define a game. You should clearly define what are the players, what are the action space, the payoff, all those type of things. I mean, it's fine that we can model uncertainty, but for many real world problems, we don't have. There are lots of things we don't know at all, so we're not able to make a good model. That's number one. Number two, if the problem is very large scale, so oftentimes it's difficult to solve. Come up an efficient algorithm with performance guarantee, with some bounding in terms of how far it is to the real equilibrium, those type of things. Number three could be if the problem is non-convex and there isn't a way to approximate that problem. So oftentimes we're not able to design algorithms with performance guarantee. And another thing is, I guess we solve lots of games. We come up with efficient algorithms because sometimes there are some domain structures which could be exploited, so that we're able to exploit that and come up with efficient algorithm to solve real world problems. But for some problems, there is no such a thing. And so it's very challenging to design good algorithms with performance guarantee. So I think for those problems, we might look into RL. And I guess one more thing is multi-agent RL or RL is receiving increased attention. And I think this is, I guess RL is currently the hottest topic in AI after AlphaGo. Um, so I think it's achieved significant performance in many domains, especially robotics and games. And I will show you later, it works well in many real-world problems as well. So I guess earlier days, people talk about single-agent RL, where and now sometimes there might be multiple agents. The agents might collaborate, might compete with each other, and then we have to design in RL algorithms so that a team of agents they could reach some equilibrium or reach global optimum policy. And there has been increase in many different algorithms and has received increased attention. And there are lots of tutorials online and lots of industry like DeepMind. There are lots of people work on this direction as well. So I think in my view, it's received increased attention. Um, I guess this does not mean that multi-agent RL or RL can always work. Even we see the above, those problems are, I guess, problems with the pictures. Maybe RL can work, but actually it's difficult to design good RL. So we are doing some related work. For instance, we're applying RL, try to solve very large scale games. And we're there's some problems we're not able to make good progress at this moment just because it's still very challenging. So I think in the rest, maybe 20 minutes roughly, I will quickly go through some of our recent work on applying RL to real world problems. And those problems include including games, for instance, including security, e-commerce, urban planning, so different domains. And in some domains, there is very tough computation. And in some other domains, there is no such very tough computation. And in some domains, we have lots of data. And in some other domains, we don't have any data. So for all those different situations, we're able to apply RL to get a good solution. So let me start with something we did last year about Bridge. Bridge is another game which so as compared with two-layer poker, Bridge is more complicated because Bridge has 4 players. There are 2 teams. Like here, those 2 red dots representing one team with 2 players. So for Bridge, even the 2 players they work together, but they are not able to communicate during the game. So they still need to reason about each other. So there is international competition on Bridge, and there are lots of softwares available on the internet. So I guess our aim is trying to come up a good Bridge player. So I guess this shows our architecture. So basically, we're using RL. So the architecture is somehow similar to original AlphaGo in the sense we also use human knowledge, human playing history to come up an initial policy, and we also do self computation to improve the performance. But here we're not using actor critic framework, and which we found it's not working well, and we directly use policy grading. But we have another network because here we have each player has a teammate. So for each player, we have another neural network which is used to predict its teammate cards, which is kind of reasonable. So there are still lots of tricky things here in our approach. For instance, we have to come up, because there's very large state space, we have to come up very compact building sequence representation so that we're able to improve the efficiency of the training. So in the end, we're able to beat the best player of it at this moment, which is W Bridge 5. This is the best player in the world over the last few years. So this is what we did for Bridge. Basically, Iorio can work. And we also work collaborate with industry to solve their problem. One problem we have been working with Alibaba is to fight against a fraud transaction in e-commerce. There's a big green industry in e-commerce, which is a fraud transaction. So the problem here is that so for Alibaba, if you're a seller, you hope that when the user is searching some products you are selling, you hope your product will be showing on the search web page. So Alibaba is using some ranking algorithm to decide which product will be showing on the search web page. The search outcome. There will be list of products. So obviously you want to improve your chance. So if your product has very good sale, has very good reputation, your chance will be higher. But another way is you could do advertisement with Alibaba. So you pay Alibaba money, and they will take that into account and maybe put your product on the first page and good position. Now there are some other company or they're doing fraud transaction. So basically what they do is they will do lots of things trying to influence or manipulate the ranking algorithm by Alibaba. So those companies will talk to you and ask you, you don't need to pay Alibaba to do advertisement. You might just pay little money to me and I can do something to improve your chance and can even do much better than doing advertisement. So basically, I think the ranking algorithm, there are some patterns. So those those companies who are involved in fraud transaction, they're able to do something. For instance, they do some fake transaction. Everything is real. But even they will mail, they will ship something, but the box is empty. They will make a payment, but later they will return the payment back. All those type of things. Fake click, that will have an impact on the ranking algorithms as well. So basically, they are doing whatever to do to manipulate the ranking. So that's a problem. Which so there's a game between Alibaba and those companies who are involved in fraud transaction. So we did two things. One is we try to learn a good policy for Alibaba to penalize those companies who are those sellers who are involved in fraud transaction. I guess the long-term goal is we want them to feel that if they're getting involved in fraud transaction, their reward would be less as compared with honestly selling their stuff. So we use deep RL to train a good policy. I guess because of time, I will not go to the details. And another thing we did is Alibaba is using some deep neural network to decide whether a transaction is fraud transaction or not. I guess why those people can still manipulate, because they're doing something try to manipulate this neural network, this classifier. So we directly attack this neural network. And if we're able to find out some adversary examples, then we can use those adversary examples in training and improve the robustness of the classifier. I think here, even adversary training, those types of things are widely started in computer vision. But if you want to apply those to those e-commerce, those techniques cannot be applied, because here pretty much everything is discrete. So any gradient-based approach will not work. So we need to come up efficient algorithm to, even the framework is the same, but we need to come up algorithms really to find out those anniversary examples and do anniversary training to improve those biases. All this work have been deployed in the real system. So there are some other things we have been working on urban planning. I guess the first problem we look at is kind of ERP pricing. So this is something in Singapore. I'm not sure whether US has this. Basically, if you go to some let's say downtown during rush hour, you have to pay extra money. So there is something on the road. If your car goes through that, so you need to. So in Singapore, every car has a chip, and also you need to put a cash card there. So there's certain money would be automatically deducted from your cash card. So actually, it's quite expensive. Sometimes you need to pay about $7 or $8 when you go through certain parts of the city. And now everything's static. So we know, 5 months later, certain period, if we go through somewhere, how much we need to pay. So I think this is not good enough, because sometimes, for instance, and certain time, even it's rush hour, due to some reasons, downtown is empty. Because of the high price, all the cars might try to avoid going through downtown, which is not good, because the government want the best use of public resources, such as roads. So in that situation, it's kind of wasting of public resources. So I think maybe we can use some dynamic ERP. So the pricing could be dynamically changing. For instance, every 15 minutes, 10 minutes, we can update the price. So if the cars are using GPS, they could, based on the new price and the driver's preference on whether they're sensitive to money, they might suggest a new road, and so that we're able to improve the traffic situation. So this is kind of very complicated planning problem, because we have to model how all those cars will change their behavior, and their behavior change will change the traffic. And we have to model all the source, destination, all the uncertainty, all those types of things. So we can easily model this as large scale problem DP problem, but we're not able to exactly solve this. At the beginning, we use RL with function approximation, and we're only able to solve the problem in downtown. And I guess last year we came up some multi-agent RL, where we divide, let's say, Singapore into many small zones, and in each zone, there's an agent in charge of the pricing in that zone. Why multi-agent RL can work? Because for those traffic problem or transportation problem, there's some kind of local influence. So the traffic in one area might only affect its neighboring areas in a shorter, in the near future. So that's where we're able to take advantage of those more distributed RL algorithm, and so that we're able to learn a good policy. So that's something we did for using multi-agent RL, with some other ideas, trying to learn good policy for very large scale planning problem with lots of uncertainty. So we also did something with Didi last year. Didi is Chinese Uber. I think in terms of the number of customers, it might be even bigger than Uber. So the problem we're dealing here is how to decide the bubble price. So basically for Didi, how it works is, if you're a user, you type a destination, and then Didi needs to come up a price, which is estimated price about roughly how much you will pay if you want to use Didi service. And if you feel the price is acceptable, so you will say yes, you want to use it. Then Didi will then match a car with you. and then later the car will drive you to your destination. So the current approach for DD, this pricing part and later the management part, they're totally separate. They're using separate algorithm to dealing with those. Actually, it has to be optimized together. I guess there are lots of good reasons for that. Because of the time I won't talk about that. I guess what we did, we tried to solve an overall problem together, but still we're using some kind of disputed idea for the bubble pricing part. We're using contextual bandit to solve that problem, and the bandit algorithm will take the mentioned algorithm the outcome as the reward function or the reward signal for the bandit part. So I think the approach has been tested in few cities in China already. So that's for urban planning. And actually we have some other work to learn a leader policy where there's a leader and the leader could take some action to affect many followers. And here we assume the followers, they're self-interested. So the question here is, how can you compute a good leader policy? And this is quite challenging. One is the followers are self-interested. They're competing with each other. And also, when the leader wants to make a decision, they have to think about how the followers will respond. So that's why it's very challenging. And we have been working on solving this type of games, but here we're trying to use RL to compute a good policy. So we came up some approach based on event-based RL. So basically we try to, given our policy, we try to predict what trajectory would happen, and then directly optimize over that trajectory. In this process, we also model how the follower will react to the leader's policy. And there's lots of scalability problems, so we use lots of abstraction to improve the scalability, where we have formal results as well to show that this algorithm will converge with some bound. We recently did some work on kind of hierarchical RL. Basically, hierarchical RL, there's a high-level policy which will be updated less often as compared with a low-level policy. I guess there's one big challenge for hierarchical RL, which is that the high-level policies suffer from the non-stationary problem, because the low-level policy will change, constantly change, leads to different state transition and the rewards of the high-level policy. I guess the key idea here is for the high-level policies training, we take into account the low-level policy. So we put the low-level policy as part of the state space of the high-level policy. So the high-level policy is conditioned on the low-level policy. I mean, it's a very intuitive idea, and which leads to significant better performance as compared with the existing hierarchical RL approach. We also think about how to, for multi-agent RL, how to come up with the best communication policy. So in lots of domains, there is a constraint on the communication. For instance, for robot soccer, as one example, I think there's a rule, for instance, during every 1 minute, you can only send 10 bytes of message to other robots. So they just use this to model in the real world soccer game. Actually, we don't have much time to communicate with each other. Because if these robots can send whatever they can send, then pretty much it can become a centralized planning problem. So there are many other domains where the communication is really limited due to many physical constraints. So in such kind of a situation, so we have to make lots of decisions. For instance, you need to communicate with whom, and when to communicate and what to communicate. So those are the problem we try to solve. I guess in our work, we convert the constraint on communication or bandwidth constraint to the message entropy. We prove there's equivalence between the limited bandwidth and also the entropy of the message. And then the idea became we want to compress the communication message, and we use information bottleneck as an idea to train such kind of policy. And in the end, we are able to build a state of the art. So one thing we just did recently is about some kind of intelligent light. So I guess this is in collaboration with a company. They're doing smart devices. So we're thinking about the future. We might have smart light, or I mean, all equipments could need to be smart. So take a light as one example. I guess we have different people are different. We have different preference of light level. And also our preferred light level might change with different activities we're doing, or the indoor temperature, outdoor temperature, outdoor light, all those types of things, and how many people are in the room. So we're thinking about whether we're able to design some such kind of algorithm which can suggest the light can automatically change, learn the preference of the user and change their light level so that to satisfy the user. I guess that's the problem we're thinking, and I guess this is challenging. Number one, people are different. We don't know their preference model. So preference model means and different state, what's their best light level, I mean their preference. And also people, I guess for this learning problem, the only feedback we can get is users' feedback. For instance, if a user feels the light level is not good, they will just manually change the light. And different people will be different. For instance, if for me, if the light level is slightly different from my preference, I may just still will not change it because I need to go to the door and do something. So we have to model human behavior as well. So there are lots of parameters to learn during this process. And also we need to quickly learn the good preference. And for instance, if you a new user, if a few suggested light level are not good, so the user might get tired, may not like the product anymore. So I guess that's a problem we're trying to address for such kind of learning problem and decision-making problem with lots of uncertain parameters. How can we quickly learn that and make the best decision? So we did this and did experiments in both simulated environment and real environment. I think, so we also, I guess, we participated in some kind of mini StarCraft competition. So this is Microsoft virtual environment. So the game is small scale, where there are two players. So and the two players need, each team design one player, and the other player is designed by another team, which you don't know. And there is a competition in the sense, the first player who goes to the exit door will get 3 points. And there's a collaboration. If two players work together, your chance of catching the pig is significantly higher. If you can catch the pig, every agent will get 25 points. And also in this competition, there are lots of uncertainty. For instance, we don't know how the pig is moving. Also, we every time we get some information about where is the other player, where is the pig, and that information could be wrong as well. Another thing which is significant challenge here is we have to learn very efficiently. Different from like AlphaGo, we can run billions of games to learn good policy. Here we cannot do that because the simulator is very slow. So I think we need like more than 10 seconds to run one game, and the space is still huge. So you really need to very efficient learn good policy, which is a new challenge. So we came up solution based on learning and lots of game theoretical reasoning and optimization techniques as well to beat the more than 80 teams from 26 countries. So I think my time is over. I'm trying to summarize here. I think I'm working on more complex AI problem. In my opinion, there are lots of big breakthrough over the last few years. Their problem is still simple in the sense. What I mean by complex problem is that the environment might be stochastic, or even we don't know how to model it. There are many different players. They might compete with each other, and we have to make a sequential decision. And sometimes we're not able to train the policy offline. We have to do online training, and we have to do distributed optimization. So there's lots of good examples which have all those type of features. There are many. For instance, StarCraft is still open challenge. Like for Army. I guess those will be the future as well. There are still lots of open challenges. I think RL would be the right solution to solve those problems. But there are still lots of challenges. For instance, scalability is one. So if there are thousands of agents and those agents are heterogeneous, so how to improve the scalability is still very challenging. Robustness is another one. For instance, we're working with lots of industry partners. We often have this issue. We can use some data to train policy offline, but if we want to get a good online performance, it's challenging because the online environment might be different, or everything is changing over time, or there is lots of uncertainty. So how to improve the robustness of those RL policy is still very challenging as well. Obviously, there are lots of other issues. For instance, people are talking about where explainability, safety, all those types of things. I feel there's still a long way to go. I think that's the end of my presentation. I think I tried to show you some work we did. More apply computational game theory optimization or RL to solve problems arising from industry or arising from the society.
Thank you both for this nice, very interesting talk. And because of the time limit, let's just stop here. And you can stay for the working group formulation, right? We can definitely talk more there. So let's move on to the next talk.